So this diagram shows you exactly how you can connect three of the largest chapters that we've done this year. Thermochemistry, which is when you learn to calculate delta G. Remember, you can calculate G a multitude of ways, but once you have it, whether it's through calorimetry or theoretical calculations with H&S, maybe going home to supper, in the end you do get delta G. And you can relate delta G, which is thermochem, to equilibrium by using this equation, which we're going to talk about. Delta G is equal to negative RT ln of KQ. You can calculate equilibrium, remember the constant, by using any equilibrium concentrations, pressures, whatever, do products over reactants. Once you have that, you can either go to delta G using the equation I just spoke about, or you can go to delta E using this equation. RT over NF is the ln of KQ. Then you can get to delta E, or you can get to delta E by using the reduction and oxidation potentials. And then you can go to K using this equation that I just spoke about, or you can go to G using delta G is negative NF E naught cell. So there's a lot of ways to get between the three, but remember, AP is all about combining concepts. So you know that a question on the AP exam will look like equilibrium, and halfway through they'll start asking you about thermochemistry. They love to morph and combine ideas. You have to be able to do it yourself. So here's the equation that allows you to convert between delta G and E. The one thing I'll warn you is in this equation, delta G comes out in joules. Normally G is in kilojoules, so this is something to take note of. N here, N is not moles of a solid, N is moles of the electrons transferred. So when you write the reduction potential reaction and the oxidation half reaction, however many electrons is the common number between the two, after you multiply them times something, that's the moles of electrons transferred. F is Faraday's constant. It's a number. You need to know it. It's 96,500 coulombs per mole of electron. And then E cell will be in voltage, and you know how to calculate that now. To relate equilibrium constants to E cell, you use the following equation. Log K equals N. N is again the moles of electrons transferred, the common number between the reduction and oxidation half reactions. E cell, you know how to calculate, and divide it by 0.0592 as long as we're at standard conditions. So here's an example. Calculate the values of delta G naught and KQ at 25 degrees Celsius for the reaction shown below. Now the first thing I need to do is I need to split these. So I've got copper going, sorry it froze on me. So I have copper going to copper 2+, and then the other one I have Ag plus going to Ag. To balance them, I need to add 2 electrons to the first reaction, and I need to add an electron to the second one. However, to make the number of moles equal, I'm going to have to multiply the second half reaction by 2. If you go and look up their values off of the reduction potential chart, the reduction potential for the second one, because this is the reduction, the second one is listed as 0.80. Now the first one, since it's oxidation that I need, I got to look for the opposite on the chart. The chart tells me that it's positive 0.34 volts for reduction. Since I'm doing oxidation, I'm going to write down negative 0.34 volts. Now if I add them up, my E naught cell is 0.46 volts. To calculate delta G, I'm going to do negative NF E naught cell. So NF E naught cell. Now the N here, how many moles of electrons were transferred? The commonality is 2. 96,500 coulombs per mole of electrons. And E naught cell we just calculated as 0.46 volts. In the end, using 2 sig figs, because the voltage has 2 sig figs, this is a constant, and the moles of electrons are less sig figs, nor did we actually measure them, we counted them. You get negative 89,000, and remember, joules. It's joules, not kilojoules. Now, to find the other answer, because they also want you to find KEQ, so I'm going to make a little bit of space. To find KEQ, it's the log of K is equal to N, 2 moles of electrons were transferred, E cell, 0.46 volts, over 0.0592. Biggest mistake students make. They evaluate the right-hand side to be 15.54054, etc. And then they stop. And they're like, oh, I'm done, I have K. No, you don't. You have the log of K. So how do you get rid of a log? You have to do 10 to the on both sides. So you need to do 10 to the, 10 to the. That'll drop off the log, and then K will be 3.5 times 10 to the 15. 2 sig figs again, because of the cell voltage. And remember, no units for a K. Here's another one. Calculate the value of G and KEQ at 25 degrees Celsius for the reaction shown below. Now, again, I got to split it. I've got Mg solid goes to Mg2 plus, and I've got aluminum 3 plus goes to aluminum solid. Balancing it, I get 2 electrons on the first one, 3 electrons on the second one. Commonality between the two of them is going to be 6, so I'm going to multiply the first reaction by 3 and the second reaction by 2. Add them all up. Actually, it really doesn't matter if you add them up. That won't help you solve the problem. You can add them, just won't help you. So look up their potentials. Now, this one has the electrons on the right. That tells me this is the oxidation. When I look it up on the chart, I need to look for the opposite of this one. So on the chart, it says 2.37, or I'm sorry, negative 2.37. And remember, I need to flip it. But don't multiply it by the coefficient. So it's just 2.37. For the reduction potential, I just need to look it up. It's negative 1.66. Add them up, and my cell potential is 0.71 volts. To solve for delta G naught, I got to do negative N. Now in this one, there were 6 moles of electrons transferred, times F, times the cell potential. And I get negative 410,000 joules. Tells me it's non-spontaneous, since G is negative. And then to solve K, make a little room here. Log of K equals, I've got 6 moles times cell potential 0.71 volts divided by 0.0592. Make sure you do 10 to the base, or 10 as the base, I should say, power. And you get 9.1 times 10 to the 71st is the final answer. Okay, now, everything we've talked about in this chapter has mostly been galvanic or voltaic cells, but let's talk about electrolytic cells. Electrolysis or electrolytic cells are when you have non-spontaneous reactions only. Remember, non-spontaneous. You will use the following reaction or equation only for those that are non-spontaneous. What is this equation? I call it equals NFE. The I is the amps that's being applied so that the reaction will go. The T has to be in seconds, it's time, and it has to be in seconds. This is very confusing because in the 2 previous equations, N was the moles of electrons transferred. In this equation, N is the moles of solid that you're going to be making as a result of running this reaction. F is still 96,500, and E is the moles of the electrons transferred in this equation, not N. So how do you use it? We can use electrolysis to determine the gold content of a sample. The sample is dissolved, and all the gold is converted to Au3+. What mass of gold will be deposited at the cathode in 1 hour by a current of 1.50 amps? So I know it's electrolysis, and just based on the fact that they gave me amps, the only equation I know that works with that is it equals NFE. Now, here's the weird part, okay? The I is the amps, 1.50 amps. The T has to be in seconds. So 1 hour in seconds is going to be, oh shoot, I'm screwing up. I need to write up here. 1 hour is 60 minutes. And then 1 minute, 60 seconds. And you're going to get 3,600 seconds. And we're going to be solving because, and I know that because I'm doing mass of gold. Gold's a solid. F, 96,500. The hardest part for students is E, figuring out how many moles of electrons are transferred. The key is you have to be able to interpret it. You're taking gold, 3 plus, terrible color I chose. You are taking gold, 3 plus, and you're turning it into gold solid. So to do that, how many electrons would you need? 3 moles. That is what you have to be able to do to solve this question. So it's 3 moles of electrons. When you solve for N, I get 0.0187, and that is going to be my moles of gold. But remember, it doesn't ask for moles, it asks for grams. So 0.0187 moles of gold. Every mole of gold is 197.0 grams. And in the end, I get 3.68 grams of gold. And if you're wondering where I got the 197, it's from the periodic table. It's its molar mass. So here's another one. What mass of aluminum can be produced in 8 minutes by passing a constant current of 100 amps through a molten mixture of aluminum oxide? So again, amps, times time. I have 8 minutes, and I need to turn 8 minutes into seconds. So 8 minutes, every minute, 60 seconds. And so I get a grand total of 480 seconds. And 96,500. And how many electrons? Again, the hardest part. If you look at this equation, they're talking about aluminum. You're making aluminum. The aluminum is coming from a mixture of aluminum oxide. In aluminum oxide, what's the charge of just the aluminum? I don't care about the oxygen. The aluminum in aluminum oxide is 3 plus, and I'm making aluminum solid. So how many electrons do I have to add? 3. So the answer is 3 electrons, 3 moles. Solve, and I get 0.166 moles of aluminum. Doesn't want moles, it wants mass. So 0.166 moles of aluminum. Every mole of aluminum is 27.0 grams of aluminum. And for my final answer, 4.48 grams of aluminum. Now there's one more thing we have to tackle in this chapter, but I promise it's the end. What would happen if it wasn't standard cell potential? What would happen if my molarities weren't 1 molar? It will change, and we have to know how it'll change. You don't have to calculate the change, you just have to know how it will change. So here's an example of a cell reaction, and its potential right now is 1.36 volts, which tells me right now it's spontaneous as written. So as this direction, it's spontaneous, it happens on its own. What will happen to the cell potential if the cerium 4 plus is greater than 1 molar? Well, we can use 2 ways, Le Chatelier or Q. If you increase the cerium 4 plus concentration, Le Chatelier says if you increase, you'll shift away from that increase. So you'll shift right, which means you'll be going along with the spontaneity of the electrons. That means the cell potential will get more positive or more spontaneous. On the other hand, if you were to increase one of the other concentrations from the right-hand side, like if you were to increase this one or this one, you'd be going to the left, away from the spontaneity, so it would actually decrease its potential. Like I said, you aren't actually required to calculate anything, but the Nernst equation is the way that you do calculate anything that's not standard cell potential. And this is the equation, but all I want to point out to you is the following. E cell here is non-standard. Notice it doesn't have that little naught symbol. And it's equal to the standard cell potential, and then it takes into account the differences. Mostly, it looks at Q. Remember, Q is the same thing as K. It's products over reactants. The only difference is you don't have to have the concentrations at equilibrium. So we're going to do this. We're going to think about it and figure out how this answer will change, but we won't actually calculate it. So to decide if the potential is going to go up or down, you can either do what I did on the previous slide where I used Le Chatelier, or you can also use Q. And you really need to know both because sometimes one answer will help more than the other. Remember, Q is products over reactants, just like K. You cannot include liquids and you cannot include solids. If the Q is going to be greater than 1, then the potential will decrease because you're going to be subtracting a number from that E naught cell. If Q is less than 1, then the potential will actually increase. So here's an example. Consider the standard galvanic cell based on the following half reactions. Now, keywords. It's galvanic. As of right now, what I know is it's spontaneous. They give me these two half reactions, but all I notice is they're immediately both reductions. That's impossible. One of them has to be the oxidation, so I got to figure out which one's which. Before I can do anything, I need a reaction. If you look up their values on the chart, this one is listed as 0.34, this one listed as 0.80. So to make it standard, or spontaneous I should say, which one should switch? This one. It's less positive, it's less likely to undergo reduction. So if I flip it, I get Cu, Cu goes to Cu2 plus 2 electrons, and that's negative 0.34. The other one is still Ag plus E minus makes Ag 0.80 volts. Add them up, and I get a grand total of 0.46 volts. But that's really not my focus right now. My focus is I need a reaction. If I can have a reaction, then I can write the Q, products over reactants. So if I write it neatly, what I end up getting is Cu plus Ag, it would be 2 Ag plus, I forgot to multiply the second reaction by 2, makes Cu2 plus 2 Ag solid. So what's going to happen? First, if I was to write a Q in this reaction, I have two solids. This is a solid, this is a solid. So those being ignored, the copper 2 plus would go on the top, and the Ag plus would go on the bottom, squared, because of the coefficient. So now that I have that, let's figure out what's going to happen. In A, copper sulfate is added to the copper half cell compartment. Okay, I'm adding copper sulfate. When copper sulfate breaks down as a strong electrolyte, it'll make copper 2 plus and sulfate 2 minus. So what is that going to do? That's going to increase the concentration of copper and sulfate. Sulfate I could care less about. It's spectating. It's not even in the reaction. But the copper, if this increases on the top, my Q is going to be greater than 1. And if my Q is greater than 1, my cell potential will decrease. You could have gotten the same answer by doing Le Chatelier, because I know that this reaction is spontaneous this way. It's voltaic or galvanic. So if I increase this, I'm going to go left against spontaneity, so the potential will go down. You could have gotten the same answer two ways. The next one, ammonia is added to the copper half cell compartment. Hint, the copper is going to react with the ammonia. So if the copper is reacting with the ammonia, the copper isn't going up, the copper is going down. So if the copper is going down in the Q, then the Q is going to be less than 1, and so my potential is going to increase. And I could get the same answer by doing Le Chatelier. If this goes down on the right, then Le Chat says that the reaction will shift to the right to try to replenish, and my spontaneousness will increase because I'm going with spontaneity. Next, NaCl is added to the silver half cell compartment. Hint, the Ag plus will react with the Cl minus to form AgCl solid. So I'm copying down my reaction here, just so we can see it again. And remember, my Q is as follows. Alright, NaCl is added and the Ag plus will react with it. So if Ag plus is reacting with it, the concentration of the silver will go down. That means that my Q will go up because my denominator is getting smaller. And if Q goes up, then my potential will decrease. You can do the same thing here. If this goes down, I'm going to shift to the left against spontaneity, so it will go down. Now the only one where it really is not going to help you to do both methods is this next one. It says water is added to both half cell compartments until the volume of the solution is doubled. Remember, if you add water, you're diluting it. If you assume that before the dilution that they were both 1 molar, 1 over 1 squared is 1. But if they're both diluted after, you would think it would have no effect. But let's just say they're cut in half. So the new concentration is a half on top and a half on the bottom. When you divide that, you actually get 2. So Q is going up. And if the Q is going up, then the potential is going to decrease. And that would not have been easy for you to do with Le Chatelier's principle. The last one, the silver electrode is replaced, there's going to be no change. Changing the solid that's involved is not going to change the concentrations of the ions, so it will have no change on the cell potential. And that, my friends, is the end. Finally.